And Arena, you can take it away.
Happy New Year, everyone. It's my pleasure to introduce the first speaker for 2023, Matt Mastroeni. He's been working on Koszul algebras and will give a talk on Chow rings of matrix R Koszul. Matt?
All right, thank you. So first of all, thank you very much to all the organizers for giving me the opportunity to talk about this to such a large audience. And thank you to the audience itself for coming to listen about this. I think it's a really neat result. This is joint work with Jason McCullough here at Iowa State. And I'm just really excited to tell you about Koszul algebras. So let me tell you a little bit about the plan for the talk. So I've kind of divided things into 3 parts. So in the first part, for people who are maybe a little bit newer to commutative algebra or don't necessarily work a lot with Koszul algebras, I want to try to convince you thoroughly that Koszul algebras are an interesting class of rings that are really worth studying. And in particular, for maybe some of the grad students and postdocs in the audience, I want to highlight, or at least try to highlight, what I think are a number of open problems concerning Koszul algebras that make this an area worth working in. In the second part, we'll then specialize to thinking about matroids and their Chow rings. And in the third act, we'll put it all together and I'll tell you why Chow rings of matroids are Koszul. Okay, so for the first part of the talk, I just want to fix a little bit of notation. So K will always be a field of whatever your favorite characteristic happens to be. S will be a polynomial ring in some number of variables over that field. I will be an ideal generated by homogeneous polynomials in that polynomial ring. And R will always be the corresponding quotient ring S mod I. Okay. So this first part of the talk really is all about free resolutions. And when working over a polynomial ring, so your quotient ring S mod I always has a unique up to isomorphism, smallest possible free resolution called the minimal free resolution. So a free resolution of my ring R is minimal if the differentials, when written as matrices with polynomial entries, all have homogeneous polynomials of positive degree as their entries. And so in this case, we can extend the grading on our quotient ring R to all of the free modules in the resolution. And each free module, Fi, then breaks down as a direct sum of copies of S with various shifts. So here, this S shifted by minus J, that just refers to a copy of S where my basis element lives in degree J. And so one of the useful invariants you can get out of a minimal free resolution are the so-called graded Betti numbers of R over S. So these are the numbers, beta ij, that record exactly the number of basis elements in my I3 module that live in degree J. All right, let me give you a simple example. Let's look at K adjoin xy modulo the square of the maximal ideal. In this case, if I want to build a free resolution of my quotient ring, well, the first thing I'm going to have to do is have all of the generators of my defining ideal, x squared, xy, and y squared. And then, okay, I need to think about what are the relations on those generators. Well, with a little thought, you come up with maybe a couple simple relations. So I can do y times x squared and minus x times xy. That will give me one relation. And I can play the same game. I can do y times xy and minus x times y squared. With a little extra work, you can maybe convince yourself that these are in fact going to generate all possible relations. And then either by direct computation or the Hilbert-Syzygy theorem, since I'm only in 2 variables, I keep going backwards. You can see that the resolution stops after that. And so what we typically like to do with a minimal free resolution is we like to extract sort of all of the numerical information, and we organize this into what's called the Betti table of R over S. So the Betti table is the table having the I, I plus j graded Betti number in column I and row j. So for our example here, right, I'm going to have one copy of S in homological degree 0. That's this one right here. Whereas I have 3 copies of S in degree 2 in homological degree 1. So I put that in column 1 and row 1 because the row and the column have to add up to the degree, which is 2. And then finally, those 2 copies of S living in degree 3, that goes in column 2 and row 1. All right, so there's lots of useful invariants that you can pick off the Betti table of your ring. So for example, the regularity of your ring, so that's just the height of the Betti table. In this case, I have to go 1 row down. The projective dimension is the width of the Betti table. So in this case, I have to go 2 columns over. And I can also get other useful invariants. I won't say too much about this, but I can also compute the Hilbert series. Right, so this is sort of telling me the numerators of all my fractions here, the 1, 3, and the 2, and then the degrees that they show in, they're telling me what powers of t to multiply by. All right, so another, probably one of the most important examples of a minimal free resolution is the Kazul complex. So if I take a polynomial ring in 3 variables and I kill those 3 variables, so I get the ground field again, I get this for my Kazul complex, and this provides a minimal free resolution of K over my polynomial ring. So Kazul complexes are nice for a number of reasons. So we can think of them sort of as coming from iterated mapping cones for one thing. They're nice finite resolutions. But from this perspective of Betti tables, they're nice because all of my Betti numbers line up in just 1 row of the Betti table. And what that's corresponding to in the resolution is the fact that all of my differentials, they just have linear polynomials for the entries of the differentials. And so if we were going to move beyond the polynomial ring case, well, we might lose the fact that our resolutions are finite in general. But if you were kind of hoping for what's the next most natural case after polynomial rings, one thing you might want to insist on is that the Betti numbers or the differential in your resolution are simple the way they are in the Kazul complex. And this is exactly the idea of a Kazul algebra. So my quotient ring R is Kazul if, when I look at the homogeneous maximal ideal, the quotient by the homogeneous maximal ideal has a linear free resolution over R. So polynomial rings give an example of Kazul algebras because the Kazul complex gives a linear free resolution of K in this case. You might naturally wonder, are there any other examples? Well, yes, you have to look no further than K adjoint xy modulo the square of the maximal ideal. In this case, right, so if I want to build a free resolution for K, my first map is going to consist of the generators of the maximal ideal, x and y. And then I need to think about, okay, what are the relations on things that kill x and y? Well, because the square of the maximal ideal is 0 in my quotient ring, I'm going to have one syzygy that looks like x and 0. I'm going to have another syzygy that looks like y and 0 because both x and y kill x. And I'm going to have 2 similar syzygies for the things that kill y as well. And it's not terribly hard to convince yourself that, in fact, these are all the possible syzygies I could have. So this is the next step back in my resolution. And this process is going to continue, right? So at each step, each syzygy is going to be annihilated by both x and y. So I get 2 more syzygies corresponding to each syzygy. And so I have this doubling in the number of syzygies, but at each step, they're all linear syzygies. And so this is a Kazul algebra. Okay, so that answers the question of what is a Kazul algebra. But then the next question should be, why the heck should I care about Kazul algebras? Why are these things worth studying? And so maybe a first reason that you should care about Kazul algebras is that they have a nice duality theory. So it turns out that every Kazul algebra, as long as the defining ideal doesn't contain any linear forms, and if they do, you can just kill them off and get a presentation over a smaller polynomial ring. If that's the case, then in fact, your defining ideal always has to be generated by quadratic polynomials. And so every Kazul algebra corresponds to what's called a quadratic dual algebra, or Schriek, which for free is automatically a Kazul algebra as well. Okay, but even better, using this quadratic dual gives a canonical way to construct the minimal free resolution of K over your Kazul algebra. And so how does this work? Well, the free modules in your resolution, they are going to look like your ring R tensored over K with the K duals of graded components of the quadratic dual. So in essence, these graded components of the quadratic dual are telling me how many basis vectors for each free module. And then the differential is also quite simple. So it's just multiplication by a particular element in the tensor product of R with its quadratic dual. Now, the first time you see this, this might seem a little strange. Why the heck would you do this? But again, I want to point out this is kind of very natural if you start by thinking about the polynomial ring case. Because as it turns out, right, polynomial rings are Kazul. Their quadratic dual turns out to be an exterior algebra in the same number of variables. And so if I have an exterior algebra, say in n variables, I'm not going to have graded components in degrees higher than n. So this is going to turn into a nice finite resolution. And after choosing bases and writing down kind of the maps appropriately, what you recover is exactly the Kazul complex. And so kind of Kazul algebras are, from this resolution perspective, kind of exactly the right generalization of how things work over a polynomial ring, just you might be dealing with infinite free resolutions now. All right, so an immediate consequence of this. So if I'm interested in the Betti numbers of K over my Kazul algebra R, and I want to write down the generating series for this, which is called the Poincare series of R, well, those ranks of my free modules, they're given by exactly the graded pieces of my quadratic dual. So this turns out to be exactly the Hilbert series of the quadratic dual. And so if you're interested in computing Betti numbers, well, this gives you potentially a way of getting a handle on that. You just have to compute a Hilbert series for the dual. Another way of thinking about this is just by virtue of having a linear free resolution, this is going to say that your Poincare series times your Hilbert series with an appropriate little twist where I replace t with minus t. The product of those two formal power series is going to always be equal to 1. And so concretely, right, what this is saying is if you want to compute Betti numbers, all you have to do is be able to formally take the reciprocal of the Hilbert series, which, right, this is the Hilbert series of my Kazul algebra R, not the quadratic dual. So this is something that I can very easily compute, say, from a finite free resolution over a polynomial ring. And so this is much more easily computable. To give an example, go back to polynomial ring in 2 variables modulo the square of the maximal ideal. So here it's not hard to see that the Hilbert series is going to be 1 plus 2t. I've got basis vectors or basis monomials 1, x, and y. And so if I just replace that t with a minus t and take the reciprocal, I get this nice geometric series, which exactly accounts for the doubling in the number of syzygies that we saw earlier. Okay, so keeping with the theme that kind of Kazul algebras are this nice natural extension of what happens over polynomial rings, I wanted to highlight this result, which I think is probably one of the nicest structural results on Kazul algebras to come out in recent years. This came out of the Women in Commutative Algebra conference. And it says basically that you can take that construction, that canonical construction for the resolution of K over your Kazul algebra, and you can modify this to in fact give minimal free resolutions for every single power of the homogeneous maximal ideal. And not only that, just like over a polynomial ring, these resolutions turn out to be a linear resolutions. So you go down to degree A for the generators of the power of the maximal ideal, and then they are completely linear after that, exactly as you expect from the polynomial case. And so I think this raises maybe the first interesting question about Kazul algebras. We now know kind of a couple examples of resolutions that carry over well from polynomial rings to general Kazul algebras. And so you might reasonably wonder, well, what other well understood resolutions over polynomial rings have analogs over Kazul algebras in general? I think there are possibly a number of good candidates. Keeping with this theme, so one of the nice things about polynomial rings is that they're completely characterized by all finitely generated modules having finite projective dimension. Well, that goes out the window for general Kazul algebras, but you still have something similar in spirit. So this is a combination of results of Avramov and Eisenbud and Avramov and Piva, which says, in fact, Kazul algebras, kind of similar to the regular or polynomial case, are characterized by all finitely generated modules not having finite projective dimension, but having finite regularity. And again, you don't have to check this for all finitely generated modules. You just have to check it for the field. Okay. So what this is saying, right, in terms of Betti tables, your Betti tables may be infinitely long, but they can't be too bad. They're always going to have bounded height. So in some sense, right, Kazul algebras, there's still a little control that you have over the free resolutions of your modules. All right. Maybe infinite free resolutions are not your thing. Maybe you say, well, I really like concrete things. I prefer just to work with finite resolutions over a polynomial ring. Well, even in that case, Kazul algebras are much nicer than general quadratic algebras. So, for example, it's known that the graded Betti numbers of Kazul algebras, so they have these sorts of vanishing. So this first vanishing is saying that in the Betti table of your Kazul algebra, all the non-zero entries live on or above that main diagonal. And in fact, it's even better because once you hit the level of the height of your defining ideal, you also have vanishing on the diagonal as well. More generally, the regularity of your ring is always going to be bounded by the projective dimension. So the Betti table will always be wider than it is tall. So you're not going to get anything pathological like these. You know, if you're interested in regularity, you've maybe seen these quadratic Mayer-Meyer ideals that can have doubly exponential regularity. That will never happen for a Kazul algebra. Kazul algebras are very nice. And in particular, so we do know some bounds on some of the graded Betti numbers in terms of the minimal number of generators defining your ideal. And there's an open question of Avramov, Kanka, and Iyengar that asks, well, does this in fact bound the total Betti numbers in each homological degree? So let me just say, this is known for a certain special class of Kazul algebras called LG quadratic algebras that I'll talk about a little later. But by and large, for G bigger than or equal to 5, this is an open question. There's also, I think, another interesting question here suggested by the two properties in the middle. So we have this nice bound on the regularity in terms of the projective dimension. You might wonder, well, can we do any better? From examples, at least, it appears the answer is yes. And I think the second property gives you an indication of how you might do that, right? So the question here would maybe be, can in fact you bound the regularity of your Kazul algebra by the height of its defining ideal? And so what I'm saying here is, if I look at my Betty table again, so we know vanishing starts on the diagonal as soon as you hit the height level. Does it actually chop off right there so that everything below there is 0? It seems to be the case in all the examples that I know of. All right, so that is hopefully a number of reasons to care about Kazul algebras, but you might also be wondering, well, do these things actually show up enough to be interesting, right? If there's not a whole lot of them, all those good properties don't do you a whole lot of good. And the answer is yes, they show up quite frequently, especially when there's either combinatorics, topology, or geometry involved. So kind of historically, Kazul algebras were introduced by Pretty back in 1970, and he was interested in them, or he defined them to sort of unify various constructions for the resolution of the ground field over universal enveloping algebras of Lie algebras from representation theory, and also Steenrod algebras coming from topology. Shortly thereafter, Froberg showed that, in fact, any quotient of a polynomial ring by any quadratic monomial ideal will always be Kazul. In fact, predating the definition of a Kazul algebra. So Tate's construction of the minimal free resolution of the ground field over a complete intersection shows that in the case of a quadratic complete intersection, that will always be Kazul. And for a more recent example, the Orlick-Solomon algebras of hyperplane arrangements. So these are quotients of exterior algebras that turn out to be isomorphic to the cohomology rings of the complement of the hyperplane arrangement. If their intersection lattice satisfies a combinatorial condition called being supersolvable, then these Orlick-Solomon algebras are always Kazul. And again, it's an open question whether this actually characterizes Kazulness for Orlick-Solomon algebras in general. And so the point I want to make here is actually there's sort of always been this nice interplay between kind of combinatorics, geometry, algebra, or topology, and Kazul algebras. So in the case of hyperplane arrangements, there's this result of Papadima and Usinski that says if you have a cohomology ring of some space that happens to be Kazul, that's actually giving you topological information about your space. Your space turns out to be what's called a rational K-pi1 space. So all of the kind of higher rational homotopy groups beyond the fundamental group turn out to be trivial. All right, so all of these examples are primarily kind of non-commutative examples. What about the commutative side? Well, on the commutative side, we've got lots of examples as well. We've got coordinate rings of Grassmannians, of general canonical curves, generic points, generic lines, Hilbert-Hebe rings of distributive lattices, Riesz algebras of principal Borel ideals. The list goes on and on. And one of the things I maybe want to point out is among a lot of these results, there's sort of an interesting intersection between the Cazul property and being Gorenstein. So if you look at a lot of these examples, right? So Kanka, Rossi, and Vala told us that quadratic Gorenstein rings of regularity 2 are always Cazul. We also know that canonical curves and Grassmannians are also always Gorenstein and Cazul. And so maybe a natural question you might wonder is, are quadratic Gorenstein rings always Cazul? Well, unfortunately, the answer is not quite. So this is joint work of myself, Hal Schenk, and Mike Stillman. I won't say too much about this because Mike already gave a nice talk about this a couple years ago, so you can go back and watch that if you're so inclined. But just to summarize quickly, so you should sort of read this like a Betty table, right? Codimensions go across the top, regularities go down the side. And for any particular regularity in codimension, you can ask, is every quadratic Gorenstein ring of that regularity in codimension going to be Cazul? Kanka, Rossi, and Vala told us the answer is yes in the regularity 2 case. If the regularity equals the codimension, that's the complete intersection case. So yes, there as well. We showed that the answer is yes in sort of the off diagonal case as well. But by and large, the answer is no. And so this is going to be important because Chow rings of matroids are very nice quadratic Artinian Gorenstein rings. It's not necessarily a foregone conclusion that these things are going to be Cazul. All right, so how do I actually show that something is Cazul? Well, if you've worked with Cazul algebras at all, you probably know that by far the most common way to show that something is Cazul is to show that it has a quadratic Grobner basis, at least maybe up to doing a linear change of coordinates first. This is what we call being G quadratic. I'll maybe skip ahead a little bit here in the interest of time, but slightly more generally, so if I have a non-zero divisor that is either linear or quadratic, then being Cazul also passes nicely back and forth between the quotient by that non-zero divisor. And so a slightly more general notion is what's called being LG quadratic. This is where you start with something that has a quadratic Grobner basis, and you kill off a regular sequence of linear forms. Now, the point I want to make here is that, in fact, all of those examples that I gave you a few minutes ago, by and large, we know they are Cazul because they either have a quadratic Grobner basis or they come from something that has a quadratic Grobner basis by killing off a regular sequence of linear forms. So almost all commutative Cazul algebras that we know of are LG quadratic, but there is at least one example that is not. And so this is an example due to Kanka. It is an example defined by 5 quadrics. That's why the case of G bigger than or equal to 5 in that open question from Kanka and Iyengar was so interesting earlier. This is a ring that is known to be Cazul, but it does not come from the standard tools that people use to prove that stuff are Cazul. It is not LG quadratic. And so you should be asking, well, if it's not LG quadratic, if the usual tools that don't apply, how do we show that this thing is Cazul? Well, they used a different tool called a Cazul filtration. So a Cazul filtration is a family of linear ideals in your quotient ring R that contain the zero ideal and the maximal ideal. And really the key property is that for every non-zero ideal in the filtration, there's some other ideal which is contained in it, has a cyclic quotient, and critically, the colon of the smaller ideal with the bigger ideal is also in the filtration. And so in particular, the colon has to be generated by linear forms. So when they introduced this notion, Kanka, Trung, and Vala showed that, in fact, every ideal in your Cazul filtration has a linear free resolution over your ring. And so in particular, since you contain the maximal ideal, that means your ring is Kazoo. All right, so this is maybe a good place to take a break. So just to whet your appetite for the future, when we come back, we'll talk about Chow rings and their matroids. And this idea, the idea of a Kazoo filtration, this is how we will show that Chow rings and matroids are Kazoo.
Any questions?
I do have a naive question. I'm afraid that the answer is going to be no, but can you go back at the slide where I think it was slide 16, where you had the Betty numbers? You were saying if R is Kazoo, then the Betty numbers need to do this. 16, I think it was.
Okay, yeah.
Yeah.
One. Yeah.
So my question would be, are there any cases where you can kind of detect the Kazoo property from knowing the Betty table, like kind of a converse of this?
Yes. So maybe one example is, well, yes. So a good case, which is maybe, let me just go ahead here. So this is one of the cases where this question is known to have an affirmative answer. This was work in my thesis. So if you're dealing with a Kazoo algebra that happens to be an almost complete intersection, which again, right, this is just a height computation. This is something you can read off the Betty table. Then what I showed was, in fact, that basically there's two possibilities. You actually get a structure theorem for exactly what the defining ideals look like. And there's two possibilities that are completely dictated by the number of linear syzygies that you have on the defining ideal. So either you have one linear syzygy and your ideal looks like one thing, or you have two linear syzygies and your ideal looks like another thing. So yes, I would say there are certainly a number of cases where I think Kazoo algebras exhibit sort of a type of rigidity more than general quadratic algebras, where having certain information about the Betty table might actually give you a structure theorem for what the defining ideal looks like.
Okay, thank you. This is very cool.
Any other questions?
I have a question. If you have a Kazoo algebra and an arbitrary module and you resolve, are the linear strands ultimately exact in the resolution? As they are exterior algebra, for example.
So could you say that for me one more time?
So you resolve a module, and at some point you look at the ijth Betty number and look at the linear maps behind that. So you ignore the higher degree maps. Is that strand of the resolution exact or acyclic, let's say?
I don't know of any good cases where something like that might be true.
True for the exterior algebra, for example.
Yeah. I do know of some work, I think of Keller Vanderboger, who was looking at kind of sort of similar to the result that I mentioned from the Women in Commutative Algebra conference. Like if you look at certain linear substrands of the pretty complex, can they give you resolutions for things that might be interesting? And so yeah, that was primarily for like monomial things, but I think that's the closest to what's known about your question.
Any other questions? Let's take a 5-minute break. So we will resume in 5 minutes.
Can I just ask really quickly, are most of these questions sort of the same question if you're just asking them for Artinian algebras? I mean, are they the same amount as known?
I believe
Or-
so. Yes. So let me think about the various questions from.
Well, I guess,
Yeah, I don't see any case where being Artinian would give you anything more.
good. Interesting.
Matt, are you ready to resume the talk?
Yep.
Okay, let's continue.
Okay. All right. So, all right. So maybe just quick review of where we left off. So we had left off with this technique of a causal filtration, which was how Kanka had shown that this example of something that did not come from having a quadratic Grobner basis was causal. This is going to be sort of the key construction for how we proceed with Chow rings of matroids. Okay, so let me tell you a little bit about matroids and their Chow rings. So I won't give you a formal definition of what a matroid is, but for all intents and purposes for this talk, all you really need to know is that a matroid is a simplicial complex M on some finite ground set E that generalizes notions of independence in algebra, geometry, and graph theory. And the elements of our simplicial complex in this context, we call them independent sets. So the example that you should keep in mind as far as having intuition about matroids is that any finite list of vectors in some vector space is going to give you what's called a linear matroid. So this is going to be the matroid whose independent sets are precisely subsets of that collection of vectors that are linearly independent. So if I have some collection of vectors in R3, I can ask which subsets of those vectors are linearly independent. And just like if I have a set of vectors, right, one of the things we like to do is ask, well, what is the span of that set of vectors and what's the dimension of the span? Well, you can do something similar in an arbitrary matroid. So if I take a set F, that's a sub of the ground set of my matroid, the rank of that set is just going to be the maximum size of an independent set contained in F. The closure of that set is going to be all the things that I can add in the ground set to my set F without increasing the rank. So these sort of play the analogs of dimension and span respectively for an arbitrary matroid. And the star of today's show is the idea of a flat. So these are all the subsets of the ground set that are equal to their own closure. These are like the linear subspaces associated to your matroid. And just like the set of subspaces of some vector space, the set of flats of a matroid forms a lattice when ordered by inclusion. And it's a graded lattice graded by the rank of the flats. So if we go back to that collection of vectors in R3 that I showed you, lattice of flats looks as follows. So I get a flat corresponding to each linear subspace spanned by these vectors. So 4, V4, V5, right? They span the same line. That's going to give me a rank 1 flat in my lattice. Whereas the flat 1, 2, 4, 5, that's going to correspond to the XY plane. 1, 3 corresponds to the XZ plane, and so on and so forth. All right, so here's a slightly more complicated example that I want to use as sort of a running example for the rest of the talk. So I'm going to look at the linear matroid coming from asking whether the columns of this matrix are linearly independent. In this case, one thing you might notice are that any 3 columns of this matrix are linearly independent. And so that says any 2 subsets of columns will be a flat because I can add anything else and the rank will go up. However, right, if I look at the first 4 columns, those are linearly dependent. So that's going to give me a rank 3 flat. Whereas if I take the last column and any other 2 vectors, those will also be my other rank 3 flats. Okay, so I need to tell you about 2 operations that you can do to take an old matroid and produce a new interesting matroid. That these will be useful for later. The first of these operations is what's called truncation. So if I have my matroid M, its truncation is the matroid that I get by defining a new rank function where I take the minimum of the original rank of my flat against the rank of my original matroid minus 1. So the key thing to know is what this does to the lattice of flats. And what it does is it takes all the hyperplanes in the lattice and just chops them out. So here by hyperplane, I don't mean hyperplane in the sense of like a hyperplane arrangement or anything. I mean the flats of submaximal rank. So in this case, I'm looking at the rank 3 flats. The truncation is going to just chop those out of the lattice. So that's my first operation. The other operation that I need is what's called restriction. So I can take any matroid and restrict it to some flat. And in this case, you'll get the matroid whose independent sets are precisely the original independent sets that happen to be contained in your chosen flat. What this does to the lattice is it restricts to the interval of all things that were underneath your chosen flat in the lattice. So if I take my lattice here and I restrict to the flat 1, 2, 4, I'm going to get everything that was under 1, 2, 4 in my lattice. Okay, so that's the combinatorial background. With that out of the way, I can now tell you what the Chow ring of a matroid is. So the Chow ring of a matroid, this is honestly the Chow ring of some smooth toric variety, but you don't need to worry about that because it has a really nice combinatorial presentation. So this is going to be a quotient of a polynomial ring whose variables are indexed by the non-empty flats in the lattice, modulo a Stanley-Reisner ideal generated by square-free quadratic monomials corresponding to incomparable flats in the lattice, plus some linear forms that you get by summing over all flats containing a particular rank 1 flat. Let's look at an example. So if I look at the uniform 2, 3 matroid, so this is a matroid whose independent sets are all sets of size at most 2 in a set with 3 elements. Its lattice of flats consists of just the individual elements and the entire set and the empty set. And so the incomparable flats are just going to be the flats of rank 1. So I get 3 quadratic monomials, x0, x1, x0, x2, x1, x2. And 3 linear forms that I get by summing over all the things that contain each rank 1 flat. All right, so for this example, you'd probably suspect Chow rings of matroids are not that bad. This is just a rank 2 matroid. What about our running example, which was rank 4? How bad could that be? Well, this is the defining ideal of our running example, which is just to show you, right, even in rank 4 on a ground set of 5 elements, these ideals get pretty big, pretty darn fast. And so deducing algebraic properties of these rings is not going to be a walk in the park. All right, so why care about Chow rings of matroids? Well, so there are kind of a number of purely combinatorial conjectures about matroids. Probably one of the easiest ones to state is called the Dowling-Wilson top-heavy conjecture. And that conjecture simply asks, if I want to count the number of flats of a given rank K in my matroid, in a certain range, can you say that there are more flats of higher rank than there are of lower rank? Very simple question, very simple inequality, very hard to prove. And in fact, it was only resolved recently in 2020 by Braden, Mathern, Proudfoot, and Wang using an augmented version of chow rings of matroids. Chow rings of matroids were also used to establish a number of other purely combinatorial conjectures about matroids as well, including the Heron-Rhoda-Welch conjecture. And sort of the proofs of all of these statements rely heavily on showing that chow rings of matroids have a number of good algebraic properties. Namely, they satisfy Poincare duality, the Hard-Lefschetz theorem, and the Hodge-Riemann relations. So from a purely commutative algebra perspective, these are really nice quadratic Artinian Gorenstein rings. And in particular, these chow rings also fit into a much larger framework. Let's see, there's a question in chat. Can we somehow make the quadratic relation 0 disappear by multiplying each xf with a bunch of idempotents? I'm not sure how you're going to get idempotents in a quotient of a monomial ring or a quotient of a polynomial ring without forcing some relations that are not homogeneous. So I don't think the answer to your question is yes here.
I meant embedding this on the bigger ring with few relations, but I don't know, it's just a random idea that might not fit.
Well, so sort of the grading is a key component to the interest in these rings. So if you embed it in a bigger ring and you sort of force these idempotents, you might be losing that grading that is actually an important part of everything. Anyway, so chow rings of matroids, they also fit into this larger framework of chow rings of smooth toric varieties associated to any finite atomic lattice and some extra combinatorial data called the building set, which generalize the wonderful models of hyperplane arrangements studied by De Concini and Cortese. And in particular, the relationship here is that chow rings of matroids are these chow rings associated to their lattice of flats with respect to sort of the largest possible building set that you could choose. Well, another big result that came out in 2020 was work of Dotsenko affirmatively answering a 15-year-old question of Manin that the cohomology ring of the Deligne-Mumford compactification of the moduli space of genus 0 curves is a Cazul algebra as well. And again, the connection here, this also fits into this larger framework. It's the chow ring associated to the lattice of flats of the matroid of a complete graph with respect to the smallest possible building set that you could choose. And so based on his work on the cohomology ring of the moduli space, Dotsenko was led to conjecture that, in fact, the chow ring of any matroid is Cazul. Now, as I told you earlier, right, just because a ring happens to be quadratic in Gorenstein doesn't necessarily going to mean that it is Cazul. So this is not obvious by any means. And previously, there weren't any large classes of matroids that were known for which this was true. But I don't think I'm giving anything away by the title of the talk. That is exactly what Jason McCullen and I were able to show for all matroids. So chow rings of matroids are Cazul. How did we do that? Well, so the first thing you might try is find a quadratic Grobner basis, because that's what everybody tries. there is a known there is a known Grobner basis. This goes back to Feichtner and Yasinski, but these are the polynomials that show up in my Grobner basis. And critically, if you look at sort of the last type of polynomial that shows up here, right, these are powers of linear forms. And so if your matroid has rank at least 3, there is no hope of this being a quadratic Grobner basis. All right, so we have to try something else. And that something else is going to be a Cazul filtration. The motivation sort of is as follows. So if you look at matroids of low rank, so if I take a rank 1 matroid, my Chow ring is just isomorphic to the ground field. Very simple. If I take a rank 2 matroid, I get something that looks like a polynomial ring in one variable modulo the square of that variable. That's Cazul because it's a quotient by a quadratic monomial ideal. In both of these cases, the Chow ring has a Cazul filtration. And in fact, they're really simple Cazul filtrations. In the first case, I just take the 0 ideal. In the second case, I take the 0 ideal and the homogeneous maximal ideal. So the idea is to use natural matroid operations, restriction and truncation, to gradually lower the rank to these low rank cases and then inductively lift the filtration. That's not exactly how the proof proceeds, but that's kind of the motivation behind the proof, at least. All right, so if you remember how truncation works from a few minutes ago, truncation takes all the hyperplanes in your lattice and it chops them out. And so if you want to use truncation to build this filtration, kind of one of the things that you're forced to do is look at what happens when I take an ideal generated by hyperplane variables and I colon it with another hyperplane variable. If I want this to be in my Cazul filtration, it needs to be generated by linear forms. And to do that, you need to impose some condition. And the condition is as follows. All right, so there's this intimidating looking coat set up here. Don't worry about what that means. I'm going to tell you how to interpret this. So if I were talking about honest hyperplanes in some projective space and I start intersecting them, right? Sort of the dimension of the intersection is going to go down by at least 1, right? In special cases, the dimension might drop a lot, but if I choose my hyperplanes generically enough, right, I expect the dimension to drop by exactly 1. And so this is what this coat set is doing right here. When I take my set of hyperplanes and I start looking at how it intersects with my given hyperplane H prime, these are the intersections where the rank drops by exactly 1. So these are sort of the good intersections. And the condition that you need is not that every intersection is a good intersection, but every intersection needs to be contained in some good intersection. All right, and so how do you make this happen, right? You can't just choose kind of sets of hyperplanes willy-nilly. Maybe I'll skip this example. We had to sort of introduce a new kind of combinatorial tool that we called a total coatom order. So this is a total order on the elements of your lattice of flats with 2 sort of technical properties, but again, it's sort of easier for me to just tell you what they mean. So the first property is basically going to force that property that you needed to have linear colons works out. And the second property is going to say that as you start intersecting things to get hyperplanes in the restriction, this construction is also compatible with constricting or with restricting. And so kind of the non-trivial combinatorics that we had to do is to in fact show that the lattice of flats of any matroid does have one of these total coatom orders. For a running example, here it is. You just read from top to bottom and left to right. And if you want to think of this, so if you want to think of each of these flats as giving you sort of a square free monomial in some polynomial ring, you can just think of this as sort of a Revlex order. It's not degree Revlex order because flats can have different sizes even though they have the same rank, but it's basically just Revlex. And so with that in hand, I can tell you how to construct the filtration. So you need two sets of ideals. So the first set of ideals is going to consist of variables that correspond to upsets in my lattice, so things that are closed undergoing up in the lattice. And then the second set of ideals corresponds to all the flats that are not contained in some particular flat F, plus an initial segment of flats with respect to your chosen total coatom order. So what we show is that, in fact, if you take these two collections of ideals and you put them together, you indeed do get a Cazul filtration for your Chow ring. And so Chow rings of matroids are Cazul. All right, so let's go back to our running example. So the first set is determined by upsets in the lattice, right? An upset is going to be determined by its minimal element, which is just a set of pairwise incomparable elements. So there are, in fact, 2,603 such sets just for this lattice. That means 2,603 ideals just in that first set of ideals. Plus you pick up a few more coming from the initial segments. So, right, just for a rank 4 example, right, you kind of have to do this abstract process of truncating and restricting. There is no hope of kind of concretely, explicitly writing down what the filtration looks like. All right, so where does that leave us? So, Chow rings of matroids are Cazul. These were Chow rings with respect to a maximal building set. Dotsenko showed that for certain types of matroids, with respect to the minimal building set, you also get a Cazul Chow ring. One of the things that we also showed that I didn't talk about is, so these augmented versions of Chow rings of matroids, we also show that they are Cazul. They turn out to be Chow rings associated to different matroids with respect to a building set that is neither maximal nor minimal. And so maybe a natural question here is, well, can you identify the appropriate combinatorial criteria on the lattice and on the building set that will give you either a Cazul or a Gorenstein Chow ring? Just to give you some indication of what might happen here. So if I look at the lattice of the uniform 3-3 matroid, so all subsets of a set with 3 elements, this set of flats is a building set, and the Chow ring has a cubic monomial in its defining ideal. So this thing cannot be Cazul, but it turns out this is the only building set that cannot be Cazul. So why this one? I don't know. So getting back to the earlier question about, like, can you do idempotence and why the grading is important? So it turns out in the augmented version of these Chow rings, there's an important graded subalgebra that sits inside there called the graded Mobius algebra of your matroid. And this graded Mobius algebra sort of carries all of the important combinatorial information because its Hilbert function records the number of flats of a given rank. And so from a certain perspective, the proof of the top-heavy conjecture is sort of about interpolating the good algebra properties of the Chow ring on the one hand, and the combinatorics that the graded Mobius algebra sees on the other hand. How do you pass between the two? And so since Chow rings of matroids are always Cazul, you might wonder, well, are these graded Mobius algebras Cazul? So this is some ongoing work joint with Karina Piva and Jason McCullough, at least in the case of graphic matroids, but largely open otherwise. We still don't know whether Chow rings of matroids have quadratic Grobner bases in some presentation. There is sort of a natural candidate based on Dotsenko's work for the cohomology ring of the moduli space, but it doesn't look too promising there. So is there some presentation that works? Who knows? And more recently, so it's been shown by Pagaria and Pizzoli that the chow rings of polymatroids, so generalizations of matroids, also have all the good algebra properties of chow rings of matroids. So they're going to be Gorenstein, they're going to have the strong Lefschetz property, they're going to satisfy the Hodge-Riemann relations. So are these things also Kuzel? Let's see. How much time do I have left? Should I?
Well, I think you shouldn't worry much about the timing. How long would you need?
Maybe just a couple minutes. I want to. So this is the coolest part.
Yeah,
I think.
Go ahead.
So, okay. So this last question is actually a conjecture posed over the past couple of years independently in different contexts by Jun Ha, Matt Stevens, Luis Ferroni, and Schroeder, whose first name I unfortunately can't remember. But it says if you look at the Hilbert series of your chow ring or your augmented chow ring, whichever version you prefer, this polynomial, because you have an Artinian ring, should be a polynomial with real roots. Now, if you're an algebraist, you might say, well, why the heck would you care about something like that? Well, it turns out that real rootedness is related to a number of combinatorial questions that combinatorists like to study. So probably the simplest version of this that we still don't know for like the number of flats of a given rank is unimodality. So if you look at the sequence of either the coefficients of your Hilbert series or the number of flats of a given rank, do they go up to a plateau and do they then come back down? So this is sort of the weakest version for the number of flats of a given rank. The top-heavy conjecture sort of comes close to this, but is still not quite full unimodality. And then there's various stronger versions called log concavity and ultra log concavity that people like to study in relation to this. So the connection here is that real rootedness implies all of these weaker conditions. In particular, it implies unimodality. So from sort of a combinatorial perspective, this is a very attractive thing to study. And there are cases where some of these stronger properties are known. So one of the original uses of chow rings of matroids was to show that the number of independent sets in your matroid of a given size forms a log concave sequence. And more recently, Ferroni, Mathern, Stevens, and Becky showed that the Hilbert series of the chow ring of a uniform matroid does in fact have this real rooted property. Now, the part I really wanted to mention was, so how does this tie all into kind of Kuzel stuff, right? So kind of the combinatorics gave us these nice chow rings to play with. It would be nice if we can give back to combinatorics a little bit. And so it turns out that there's this equivalent characterization of real rootedness. You can phrase it in terms of the minors of this infinite Toeplitz matrix all being non-negative. And it's known due to work of Polishchuk and Podsitselsky that if you're talking about the Hilbert series of a Kuzel algebra, that in fact, well, maybe not all of the minors are going to be non-negative, but a good number of them are. And so this is sort of maybe the fact that chow rings of matroids are Kuzel is sort of among the strongest evidence that we have for this real rootedness conjecture for the Hilbert series. And so the final question I just want to leave everyone with is there some homological interpretation of these remaining minors? Because if you can find that, you have an answer to this conjecture. All right, so that's what I really wanted to say. Thank you all for listening.
Any questions? Comments? Seems there are no questions. Let's thank Matt for a really beautiful talk.
Thank you, Matt.
Thank you. It was nice to see you.
Yeah, you too.
I guess you can leave now, Matt,
Okay.
Oh,
and everybody else as well, of course. Thanks a lot again.
Yeah, thank you for the invitation.
thank you. It was a very nice talk. Really nice.
Thank you. Thank you. I'm
Really,
glad
really-
I was able to share it with everybody.